Hello physics students, Dr. Berenzi here, and this is a video about Newton's second law in Unit 3, and we are dealing with a block on a table or the ground, and it's being pulled by an applied force that is being applied at an angle. We started going over problems similar to this in class today, but we didn't exactly finish the problem. We got partway there, and we got through the most difficult parts, but we didn't finish that problem up, so I want to do that now. For those of you who weren't here, this will also be an opportunity to do what we did in class today, or at least see what we did in class today. So we were trying to find the acceleration of this 4 kilogram block, and the steps that I like to go through to find the acceleration for any sort of problem that involves Newton's second law is, first of all, drawing a sketch. Then we're going to do a free body diagram. And then got to define the coordinate plane, so the x and y axes that we're going to use. And then we have to break down any vectors that don't go along those axes. Finally, we're going to use F net equals ma, Newton's second law, and then we have an equation or two that we can solve to find acceleration. So that's the overview of how we're going to solve this problem. Okay, so if I want to draw a free body diagram of this 4 kilogram block, I know that I have this 20 Newton applied force that's at an angle of 30 degrees. I have friction force that is acting against that because it gives me a coefficient of friction, so I know I have a friction force. I know I have gravitational force because this thing has mass. And I know I have a normal force because it is sitting on a tabletop. So those are the 4 forces that are acting on this block. Then I want to define the coordinate plane. I want to define my x and y axes. And it makes perfect sense in this case to make the positive y-axis point straight up and the positive x-axis point to the right. Now, if I were to draw this free body diagram on those coordinates, it would look something like this. Okay, and you will notice that 3 of those forces, these 3 forces, they already lie along one of the 2 axes, which is great. That means I don't have to break them down. But this one, this applied force, does not lie on one of those axes, so I have to actually break it down into components. I have to break it down into an x component and a y component. So to do that, I draw a right triangle. I know that this is 30 degrees. That was given to me in the problem. And then I use, of course, SOHCAHTOA, some trigonometry, and I find that if this is 20 newtons right here, then this is going to be 20 cosine of 30 degrees, and this is going to be 20 times sine of 30 degrees. Okay, what I can do now is I can replace this vector with this vector and this vector. So what would that look like? I ran out of room here, so I got to draw a new diagram on the next slide here. Let's see if we can get this going forward faster. These are just the same diagrams that we ended up with. There we go. Okay, so what that would look like is I could literally erase this vector like that, and then I just take that vector that was over here and place it along the positive y-axis. So now I have 2 axes, or excuse me, 2 vectors that point along the positive y-axis. I have one that points along the positive x, and of course gravity, friction force, normal force, those all remain unchanged. So now all my forces are pointing along either the x-axis or the y-axis. So I've broken down all my vectors. I'm done with step 4. Now I want to write F net equals ma for both the x and the y direction. Let's deal with the x direction first. So what I want to do to find F net is I want to add all the forces acting along the x direction. So, oops, I forgot F net equals MAY. So let's go back to the x direction. So I have negative force of friction because it's acting to the left, plus this force over here, 20 cosine 30 degrees, and that is going to equal mass times acceleration. The mass of the block was 4 kilograms, so I'll put 4 in for the mass, and then I have times AX. I can do a little bit of simplifying here, so I know that the formula for friction force is equal to mu times normal force, so I can replace that. I know that the coefficient of kinetic friction was given to me as 0.4, if I remember right from the last slide there. And I can simplify this into a single number, and when I do that, oops, it was 0.3, not 0.4, like I first said. All right. It looks like I've simplified this as much as I can. It's too bad that I don't know the normal force, so it appears as though I'm stuck, but remember, normal force is a force in the y direction, so I could come over here to the y direction and see if I can use this equation to figure out normal force. So let's go ahead and do that. F net is the sum of all the forces acting along the y-axis. Now, up until this point, we've been very used to writing just Fn plus negative Fg equals 0. And that has been correct up until this type of problem. But let's be careful here, because F net is all of the forces acting in the y direction. And when we broke down that 20 Newton applied force, we ended up with another force in the y direction here. So that is a force that I have to add onto this side of the equation. So don't be too tempted to write this down before you've broken down your vector, because we need to add this term right here. So this is the correct equation for F net equals ma. We don't have any acceleration along the y direction because we are on a tabletop. So acceleration 0, which is why the right-hand side of this equation is 0. Okay, I can replace this with m times g and simplify this. Those two multiplied together give me 10. These two, m times g, gives me 39.2. And it turns out I get a normal force of 29.2 newtons. Now I can take that 29.2 newtons and plug it in over here. And when I do that, I get this. Now this is an equation I can solve for the acceleration in the x direction. Unfortunately, I've run out of room, but I will get to the chase and tell you that the acceleration that I came up with is 2.1 meters per square second along the positive x direction. So that's how you'd find acceleration when you have a force that is applied at an angle. Before I end this video, I want to give you another problem that you can look at. And what I'm going to do is I'm going to give you the problem first and give you the steps that I took. So this is another problem, very similar. And let's say we are now, instead of pulling up into the right on the block, we are now pushing down and to the left. So now we're pushing down and to the left on the block with a 40 Newton force. Our coefficient of kinetic friction is 0.1, and we have a 2 kilogram block. So I want you to get as far as you can, pause this video, get as far as you can on this, and then in a few moments I'm going to silently start this and just let it roll through the problem so that you can check your work against what I have. And wherever you get stuck, you can unstick yourself and then try to solve the rest of the problem here.
check it. What's out loud?
Okay, so that's how you solve this practice problem right here. And I hope you're successful, and if not, I hope this gave you an idea of where things might have gone wrong, and I want to wish you luck on the final tomorrow. All right, bye.